Right. The previous section was working with polynomial functions. Now we're going to move on to a different type of function called a rational function. Then we're going to later look at exponential functions and logarithmic functions. So working with different types of functions, because you can encounter many different forms of functions when you're working problems. A rational function has the form of a polynomial divided by a polynomial. So it's just like the idea of a rational number. A rational number is an integer divided by an integer. A rational function is a polynomial divided by a polynomial. Polynomials have integer exponents. So polynomial divided by polynomial, it's something that we know how to work with, working with polynomials. We still have the requirement, mathematical requirement, that we cannot allow our denominator to be 0. That's going to limit some of the values we can have in our as values for our x. X could be a problem in some cases. Simplest type of rational function is the function 1 over x. If it does not have the variable in the denominator, then it's really not you don't have to worry about rational functions. It's just a normal function. But if it has a variable in the denominator, and this is the simplest one you could have, 1 over x, then it's really a rational function. If you plot that, it's going to look like this. We cannot allow x to be 0, because that's dividing by 0. That's undefined. What happens as x gets closer and closer to 0 is that this value of the function gets larger and larger. If x is positive, it gets positively larger. If it's negative, it gets larger negative. So you can make the value of the function as large as you want if you get close enough to 0. You can never get to 0 because then you'd be dividing by 0. Similarly, as you move away from 0, as the denominator gets larger and larger, the fraction gets smaller and smaller. 1/4 is smaller than 1/2. 1/8 is smaller than 1/4, so forth. But there's no value of x I can put in there to make the fraction 0. This is called asymptotically approaching a line. The x-axis is a horizontal asymptote. This graph gets closer and closer and closer, but it never actually reaches there. The y-axis is a vertical asymptote. This graph gets closer and closer and closer, but never actually reaches there. That's the definition of what an asymptote is. It's a line that a graph approaches but never actually reaches. You can get as close as you want, but you can never actually get there. This is decreasing everywhere, because you always talk about as you move from left to right. Everywhere that it's defined. That it's not defined at x0, so you have the disjoint interval where it's defined. It's discontinuous. All polynomial functions were continuous. This one is not. It has a gap there at 0. The y-axis is a vertical asymptote. The x-axis is a horizontal asymptote. If you do the check on odd and even functions that we saw previously, an even function, if you plug negative x in, you get f of x out. If you plug, if it's an odd function, you plug negative x in, you get minus f of x out. This one is an odd function. If I put negative x in, I get negative f of x out. It's symmetric with respect to the origin. If you look at the graph, kind of picture reflecting diagonally across the origin. If you do 1 over x squared rather than 1 over x, it's going to look like this. It's still going to have those asymptotes. But now, because you're squaring it, it's never negative. So no matter whether x is positive or negative, 1 over x squared is always positive. So it's always up above the x-axis. Still can't let x equal 0. And there's still no way to make 1 over x squared equal to 0. So the x-axis is a horizontal asymptote. The y-axis is a vertical asymptote. Increases to the left of 0, decreases to the right, discontinuous at 0. It's an even function. Remember, an even function is the same thing as being symmetric with respect to the y-axis. That one was symmetric with respect to the y-axis. Formal definition of what an asymptote is. If the function approaches infinity as x approaches a certain value, then we have a vertical asymptote. That's like the y-axis. As x approached 0, the function went to either plus infinity or minus infinity. So a vertical asymptote is where you get closer and closer to a value. So I'm getting closer and closer to 0 here, and my function's going to infinity. Doesn't matter whether it's positive infinity or negative infinity. It's going to infinity as I get closer and closer to 0. Either positive or negative. Doesn't matter. Either one makes that a vertical asymptote. A horizontal asymptote is defined by the fact that a function approaches a certain value as x increases to infinity. So if I go way out to the right, my function is going to come down and approach a fixed value. If I go way out to the left, my function is going to approach a fixed value. Just like these graphs here. As x gets larger, the function gets closer and closer to the x-axis, or this way. Doesn't matter which direction. If the function approaches a constant value as x goes to plus or minus infinity, that is a horizontal asymptote. So that's what vertical and horizontal asymptotes are. If we're given a rational function, then we will have asymptotes almost all the time. I guess it is possible not to have them, but most of the time you do. So the question becomes, how do you determine where they are? And depending on whether it's horizontal or vertical, you do different things. If you want to find out where the vertical asymptotes are located, you take that polynomial in the denominator. You set that equal to 0, and you solve that equation. That will give you values of x. Those values of x are vertical asymptotes. The function x equals that number. So solve take the polynomial in the denominator, set it equal to 0, and solve it. The solutions to that equation, written this way as equations, x equals a number, this is the equation of a vertical asymptote. Remember, a line has to have an equation as a definition. A line can't have just a number. It has to have an equation as a definition. So an equation of this type is a vertical asymptote. We talked about vertical and horizontal asymptotes. There's a third type called an oblique asymptote. An oblique asymptote is still a straight line, but instead of being horizontal or vertical, it's sloped. So it's going to be a straight line with some slope to it. Vertical asymptotes you always find this way. Set the denominator equals 0, period. Whatever numbers you come out with, those are all vertical asymptotes. Other asymptotes, you have to go through a process. The process is to look at the polynomial in the numerator and look at the polynomial in the denominator. Look at that highest degree term. If the degree of the polynomial is larger than the degree of the denominator polynomial is larger than the degree of the numerator polynomial, then there's a horizontal asymptote at y equals 0. So denominator larger, asymptote at y equals 0. And all you're checking is the exponents. So if the denominator has a larger exponent than the numerator, then y equals 0 is a horizontal asymptote. But if that's not larger, say they're equal, say the numerator and denominator have the same degree, that would look like this. Both have the same largest exponent. When you have this situation, instead of this, you have this. You can't have both. It's one or the other. If you have this, you still have a horizontal asymptote, but it's located at y equals this fraction. That fraction comes from this coefficient and this coefficient. Whatever these two coefficients are on that largest exponent. These two coefficients form the fraction, which is the y equals that fraction is the horizontal asymptote. Remember, y equals a constant is a horizontal line. Third possibility, what if the numerator is larger? There's only one situation when that's true where you'll get an asymptote. If the numerator is exactly 1 larger, so if the denominator is 2, the numerator would have to be 3. If it's 4 or more, then you don't have an asymptote. If it's exactly 1 more, you actually perform the polynomial division. And the ones we'll do in here, you can use synthetic division. You won't have any harder than that. But you actually perform the division, and that will give you a first order polynomial with a fraction remainder. Throw away the fraction, set that polynomial equal to y, and that's the axis, or that's the equation of your oblique asymptote. You can have more than one vertical, you might not have any. But there's no limit on how many you can have. Anything that's not vertical, there's at most one. Asymptotes are straight lines that the function approaches but never actually reaches. You can have vertical or horizontal or what are known as oblique. Oblique are just slanted lines. Rather than being straight up or flat, they have a slope to them. And the thing about asymptotes, the graph approaches them, and most of the time they will not cross. There are a couple of minor exceptions. They'll never cross a vertical, period. You'll never get a graph crossing a vertical asymptote. You can get crossing of the horizontal or oblique when you're in the middle of the graph. If you're at the extremes of the graph, it will not cross. So there are some exceptions to not crossing, not reaching. So you can have a horizontal at the x-axis, a horizontal above or below, a sloped line, or nothing. And there is at most one of those. You will not have but one non-vertical. You can have as many vertical, or vertical can have as many as, there's no limit. 0, 1, 2, 3, 4, 5. Just depends on what the solutions to that denominator equation are. So let's look at some of these situations. Here is an example of a rational function. Polynomial in the numerator, polynomial in the denominator. Let's find out what asymptotes that function has. You probably start with finding the vertical ones because they're a little easier to identify. All you have to do is you take the denominator polynomial, set it equal to 0, and solve that equation. So this is, you'd set x squared minus 16 equals 0, and solve that equation. Well, that's just a quadratic equation. Actually have, what, four ways to solve that? 5 if you count graphing. Easiest way is use the square root property. Put the 16 on the other side, take the square root of both sides. And so you get x equals 4 or x equals minus 4. Both of those are equations. X equals a constant. So those are the equations of two vertical asymptotes. There's a vertical asymptote at x equals 4 and a vertical asymptote at x equals minus 4. Remember, asymptotes are lines. They're not points. So there are two vertical asymptotes for this. Vertical asymptotes, this graph of this function will not cross the vertical, period. Okay, so those are the vertical. Let's look at non-vertical. For non-vertical, there is at most one. You can have a horizontal, or you can have an oblique, or you can have none. But only one. Once you find one non-vertical, you're finished because there won't be any more. What you have to do is you have to look at the function and compare this exponent on this the largest exponent here with the largest exponent here. So the largest one here is 2, the largest one here is 1. Denominator is bigger than numerator, right? 2 is larger than 1. That means that there is a horizontal asymptote at y equals 0. Since we have one there, there's no others. There's one horizontal asymptote at that point. So we have 3 asymptotes. 2 of them are vertical, and 1 of them is horizontal. That's all that this has. This function has 3 asymptotes. All this is asking for is find the asymptotes. For this type of question, the answer is a vertical asymptote at x equals 4, a vertical asymptote at x equals minus 4, and a horizontal asymptote at y equals 0. All 3 of those things. That would be the answer for this question. Another example, again, it's saying just find the asymptotes. So it's not asking for any kind of other solutions or anything, it's just what are the asymptotes. So if we want the asymptotes of this function, check vertical first, it's the most straightforward. Set the denominator equal to 0 and solve. So where are the vertical asymptotes for this? X equals 3. Make sure you say it as an equation. It has to be an equation because it's a line. X equals 3 is the vertical, and there's only one of them in this case. All right, what about non-vertical? Are there any? If so, what? Okay, you have to look at these numbers. This is 2, that's 1. The situations are numerator less, numerator equal, numerator 1 more than, numerator greater than that. So is the numerator less than? Is the numerator equal? Is it 1 more than? That then has an asymptote. Only that last one, where it's more than 1 greater, will there be none. Anything else, there will be 1. So this is exactly 1 more. That means we have an oblique asymptote. So we actually have to do this division. Well, here's the stuff about the vertical. There's our one vertical one. Now we're looking at the non-vertical. So divide the numerator by the denominator. Well, I think all the problems you will see, that denominator will always be that type of a polynomial, so you can use synthetic division. In this class, they will be. Later on, you could get other things. But in this class, that denominator will always be a first-degree polynomial. So we can use synthetic division to do the division here. And if I do that with these, remember to put the 0 in for the missing term. That tells me that this equals this, right? That's the result of doing the division, is you get an x term, a constant term, and a fraction. Throw the fraction away. Set the x term and the constant term equal to y, and this is your equation of your oblique asymptote. Just a linear equation, y equals mx plus b. So your answer to this problem would be that equation and this equation. Two asymptotes. So there's your vertical one. There's only one in this case. There's your non-vertical. There's always at most one non-vertical. Not a difficult job, but you have to remember what the different tests are. Vertical's easy. You just set this equal to 0 and solve. That's easy. Non-vertical, you have to compare and then choose depending on what those values of the largest exponents are. And you have 4 different situations. Less than, equal to, 1 greater, or more than 1 greater. More than 1 greater, nothing. 1 greater, this type, where you actually do the division. Equal, if it were equal, I would have taken this number over this number, y equals that, and that would have been my asymptote, if they're equal. If it's less than, it's y equals 0. Okay. How about here? Are there any vertical asymptotes? Where? X equals 3. Remember, it has to be stated as an equation. X equals 3. Are there any non-vertical? They're equal, which means the exponent, not the coefficient, the exponent. So the exponents are equal. And that means what? Means you're going to take this coefficient and this coefficient, and that will be your horizontal. There's your vertical. You take this coefficient and this one. Take that coefficient of that highest degree term and set y equals that. So your horizontal asymptote is y equals 2. Y equals 2 is the non-vertical. There's only one of those. Yes, are the 2 answers. Okay, that's how you find them. The reason for finding asymptotes is they indicate a lot about how the graph of this function is going to appear. I stated several times that a function will never cross a vertical asymptote. That means that it's going to get extremely large as you get close. That could be a very important thing to know. Thing I keep referring to is if you're trying to control a process on a factory floor, you don't want it operating near some place where the things go to infinity, because then you're going to lose control and you're going to tear up your machine and have bad product and everything else. So you want to avoid those places where you get those extremely large values. Knowing where that is important. You can also use it if you're trying to determine what happens as the input gets larger and larger. And that's where knowing how those end behaviors occur can be useful. Asymptotes can help you with that. Maybe it approaches a constant value. That's good to know. So if we're going to graph a rational function, we're still going to have to do some of the things we did previously. We're going to have to know where it crosses axes and things, or unless those are asymptotes. First thing is to find the asymptotes and plot, actually draw in, usually with dashed lines, where the asymptotes are. So find the vertical asymptotes, find the horizontal or oblique asymptote, and draw in those lines. Then you'll have a bunch of lines. And because you have those are constraints on what the function looks like. These vertical dashed lines you have, you know you can't draw a line across them. Your graph cannot cross those vertical dashed lines, period. The horizontal or oblique, it might cross it in the middle, but as you go out to very large values, it will not cross it again. Then find any values on the intercepts. You may or may not have any because they could be an asymptote. But if you can, find those. So y-intercept, x-intercepts. Now the thing about a rational function, you get the y-intercept the way you always do. You put x equals 0 in and solve. So like we went back to this one. If I want to find the y-intercept, I'd put x equals 0 in there, and so my y-intercept is minus 5 over 3. So it's a very easy thing to do. All you do is whatever the constants are. For the horizontal, the x-intercepts, because it's a rational function, all you have to do is set the numerator equal to 0. You don't have to work with a fraction. Just set the numerator equal to 0 and solve. And that will give you the x-intercepts. Now, recall that if you don't get real number answers, if you get imaginary number answers, then it does not have any x-intercepts. Okay, on this one, if you're trying to find the y-intercept, you would say f of 0, which means 2 times 0 plus 5, and 0 minus 3, which is just 5 over minus 3, or you don't leave the minus sign in the denominator, so it's minus 5 over 3. So, I'm sorry. The y-intercept is the point 0 and minus 5/3. You just, wherever x is up here, put a 0 in place of it. Oh, now this is, okay, for the x-intercepts, take that numerator and say 2x plus 5 equals 0. Set the numerator equal to 0 and solve that. And you get an x value. And so that's your only x-intercept for this one. In either case here, when we were trying to find the asymptotes, if I set the denominator equal to 0 and solve and get imaginary number answers, it does not have any vertical asymptotes. If I get real number answers, that's an asymptote. But if I get imaginary numbers, it does not have any. If I plug, if I'm doing this, if I set this equal to 0 and solve and get imaginary number answers, then it does not have any x-intercepts. If you get imaginary number answers when you're solving an equation, it does not happen. So either no asymptote or no intercept. How does the graph look? Suppose we had a vertical asymptote. Suppose we had two vertical asymptotes there and a horizontal there. Your function might look something like this. Doesn't cross these out here, never crosses these. But it gets closer and closer to this horizontal asymptote. As I go further out, it gets closer. The red ones. The blue is the actual graph. The red ones are the asymptotes. Dashed are the asymptotes. And the solid. Yeah, you should, because this helps you draw the graph. Because if you have the asymptotes in there, that's how I knew that I'm going to get, not going to go any further out here. I knew to constrain this within here and here. And I knew here I'm going to get close to here and I'm going to get close to here. That's how I knew to draw it that way. No, well, no, this is a function. It is not a parabola. It's some other function. It's a rational function of some sort. And these two are part of that. It's just the rational function winds up giving you a graph that looks like this. You can get some very strange looking graphs from rational functions. Okay, so we plotted the asymptotes, we plotted the y-intercept, we plotted the x-intercepts. Then, because it may be that your graph can cross a non-vertical, either the horizontal or the oblique, you have to find out whether it does or not. You do that by setting the function equal to this equation for the non-vertical. So your non-vertical will either be y equals b or it will be y equals mx plus b, right? It'll be a linear equation of that sort. Your non-vertical will be one of these two. So set your function equal to that. We'll see an example in a minute. It'll be maybe a little bit clearer there. But you set your function equal to that and solve. If you get a real number answer, then it crosses at that value of x. If you get imaginary number answers, it doesn't cross. Then you need to plot a few more points to help you decide how quickly something rises or falls, how quickly does it get close to those asymptotes. We're going to do an example to show all these different things. Okay, here is a rational function. We want to graph that rational function. So, first thing we want to do is what? Asymptotes. How do I get the asymptotes for this? Okay, that's if you want non-vertical. Yep. Okay, so what would you tell about that non-vertical by looking at it? What would you know about it? Okay, and what does that mean? Denominator is larger, so it's y equals 0. Doesn't matter how much larger the denominator is. As long as it's larger, it's y equals 0. So we know we have a horizontal asymptote, and there's only one non-vertical, so that's all the non-vertical. We have a horizontal at y equals 0. What else do we know about asymptotes? What about the vertical? Do we have any vertical? How do we tell? That finds the y-intercept. I'm looking for vertical asymptotes. Set the denominator equal to 0. That's normally what I do first. Set the denominator equal to 0 and solve, and you get these two numbers. Since you get real number answers, there are vertical asymptotes. These are the equations of the vertical asymptotes. So I have two vertical asymptotes, one at x equals plus 3, one at x equals minus 2. Then I go through with the horizontal, which gives me the y equals 0. So I have three asymptotes, two vertical, one horizontal. The y-intercept, that's when you plug 0 in. If I put 0 here, here, and here, the only thing I'm left with is minus 2 and minus 6. So f of 0 is minus 2 divided by minus 6, which is 1/3. So my y-intercept is plus 1/3. And let me go ahead and show you. Here are my two intercepts. My two vertical intercepts here, and I have a horizontal one right here, but it lies on top of the axis, so it's not showing. But it lies right on top of this axis. So there are three asymptotes here. One here, and one here. Then my y-intercept is right there. I just calculated that. It's at 1/3. That's my y-intercept. Now if I go back and calculate the x-intercept, I set the numerator equal to 0 and solve that. And there's my x-intercept. This is a point because it's an intercept. And I plot that, and that's right here. So I haven't done a whole lot of work yet, but I have this much information. Now just that much tells me that I'm going to be up here, and I'm going to cross the axis right there. I'm going to cross this axis right here. I know that I have to go toward either plus infinity or minus infinity as I get close to there. Same thing here and here. And since I only have, well, what I have to check, I know as I get out here, I'm not going to cross this axis. As I get way out here, I'm not going to cross this one because they're asymptotes. It's possible somewhere in here I may cross this axis because it's a non-vertical asymptote. So I have to check that. So what I do is I take the function and set it equal to this equation for the non-vertical. So y equals 0, I put whatever my rational, I put this equal to 0. I set my function equal to the right-hand side of this asymptote equation. If I do that, I'd have this equals 0. And the only way that can happen is if x minus 2 equals 0, which means x equals 2. And I already have that point because I had the x-intercept anyway, right? What that says is, yes, my graph does cross that horizontal asymptote, but the only place it crosses is at that point. It never crosses anywhere else, but it will cross right there. Because remember, this is an asymptote. It will never cross this one, it will never cross this one. It does cross this one at that one point. So there's going to be a piece of the graph between here and here. And it's going to cross this here, and it's going to cross that there. So if it's up here, and it only crosses here, that means this side has to stay above, right? So this has to go up this way, because it never crosses the x-axis over here. And as it gets close to this, it has to head to one of the infinities. The only one it can go to is the positive one. Crosses that, never crosses this again. And so then it crosses here. Since it's above here, it has to go below here, which means it heads to minus infinity here. What I don't know is what's happening out here and here. I know I'm not going to cross this ever out here, but is it up here or is it down here? The only way to tell that is to calculate some other points. So if I pick these points, that gives me that. And you can pick as many as you want. I picked a lot to make a nice smooth curve. Using Excel, it doesn't really matter. It's easy to do. If you're doing it manually, you would not do that. I would pick a point somewhere in here to get close to this to see how quickly it rises. I would get a point close to here to see how quickly this falls. Then I would pick a point just on the other side. That'll tell me, is it above or below, and how big is it? And then pick a point somewhere, maybe 2 more points here to get a curve in there. How quickly does it start flattening? Same thing over on this side. One here, and then one out here. So if I do all that, I get that curve. By picking a point here and here, you get how quickly does that go up? Does it come over and then very sharply turn up, or does it have a more smooth change? And also here, how quickly does it head that way? Over here, I have to know, is it above or below the axis? I know it doesn't cross, so I need some of these. So I need something close here and a couple more to see how much curve is there. Same thing over here. How quickly does it approach those asymptotes? You could really get by with, you need the intercepts, you need something close there. You need probably 3 points here and 3 points there. So 6, 7, 8, maybe 10 points can get you a pretty complicated curve. But this is, not an unusual situation for a rational, or an unusual graph for a rational function. Several pieces and unusual appearances. There are no general rules of thumb about, right end up, left end down, or anything like that. They don't apply to rational. They will apply in the just polynomial, but not in the rational. But those kinds of things are things you need if you're trying to graph. You need to know the intercepts, you need to know where the asymptotes are, and you need some idea of where the function is. Is it above or below, etc. That kind of information is usually sufficient for this level of analysis, where you're trying to get some general idea of behavior. So any other questions about finding asymptotes or graphing them? Next test will have some questions asking about asymptotes. It may be that you're given several graphs and asked to, or given a graph and several equations and asked which equation does this graph represent. You could be given an equation and several graphs and which graph represents this equation, etc. You could be asked just to locate the asymptotes. What are the asymptotes of this function? Which you'd have to go through those calculations, and remember, asymptotes need to be equations. So go through those calculations, come up with the equations. Those kinds of things would be possible questions concerning the rational functions.